Welcome to the Knowledge Graph seminar. Today, we are in the week 6 of the course, where our focus has been on what are some of the inference algorithms for knowledge graphs. Last week, I gave an overview of general purpose graph reasoning algorithms, taxonomic reasoning, and rule-based reasoning. Today, we have two excellent speakers with us to move that conversation forward. Martin Breven-Boer, he's going to tell us about efficient reasoning algorithms for knowledge graphs when the storage layer happens to be a relational system. And Jiakshan Yu is going to introduce us how we can use knowledge graphs in conjunction with neural networks. We are going to begin with Martin. Martin, over to you.
All right, thank you. I'll share my screen. Right, here we go. Does this come across well?
Yep.
Yeah, all right. Okay, welcome everybody. Thank you for joining. My name is Martin Breven-Boer. I work for Relational AI, and I will be talking about relational knowledge graph management systems. Okay. All right, so there's a little bit about relational AI. So relational AI develops what we call a relational knowledge graph management system, or KGMS. That's a term we're trying to coin. The term KGMS is a spin on a database management system. And it's basically emphasizing that our system is designed for knowledge graphs, but that it has the capabilities of a full-blown database management system. The KGMS uses a declarative language that we have named REL. This language has been specifically designed for knowledge graph applications. So sadly, I only have 30 minutes. I don't have time to really rigorously dive into the design of REL. So I'm going to be using some examples here and there, and I'm just going to rely on your intuition that hopefully you understand what those examples do. Yeah. So what I will be spending time on is why the system is relational, which is certainly unusual for the graph system currently, how we define knowledge, and what does it mean to manage a knowledge graph in the sense that like we have many system-related capabilities for a KGMS, but that's not really the focus of the talk. So I will only occasionally refer to like, okay, we also do this, but that is more for a system audience probably at some point. Okay. All right. So first, I'd like to briefly recap the relational model. So the relational model uses relations to represent all data. And the purpose of the relational model is to separate all the physical data representation and indexing choices from application logic. So the idea is that the application logic is completely independent of what the system itself is doing, and that the system can maximize the opportunity to execute the application logic in whatever optimal way possible. Yeah. Now, it's very important, at least to me, to realize that SQL is only one query language for the relational model. You see a different one today, which is REL. The relational model in particular should not be dismissed based on challenges with SQL for modern applications. Like we often see that people pull up like a SQL example and that, okay, this is hard to express in SQL. And they use that to then advocate for an entirely different data model. So what we are trying to do is to stick to the data model, but improve the query language. Okay.
So Martin, I got a comment from somebody saying that the volume is too low. I can hear you just fine, but if there is any adjustment you can make at your end.
I'll put my mouth closer to the mic. Yeah, is this better already?
Yes, I'm also hearing you just fine too. So
okay.
Just to let you know.
All right, thank you. Yeah, it's a little tricky to adjust anything here. So like, I'll just keep going. Yeah. Okay. All right. Okay, so let's start by looking at a very simple directed graph. So a directed graph can be represented with a binary relation, which we call edge here, and it basically contains a tuple for every edge in the graph. Like for example, this edge CA is here represented as edge CA. Hopefully that's fairly straightforward. Yeah. So property graphs can be represented as relations as well. So properties of nodes are binary relations. Like there's this movie node here that I'm going to expand on that has a title that is 127 hours. And you see that represented here as a binary relation with M and 127 hours. Okay. The labels of the nodes, like movie, this is a movie, are unary relations. That's what you see here. Okay. So now we expand this graph a bit and we introduce two additional nodes to the graph that both have two labels. Like Danny Boyle is a director as well as a producer. and he directed the movie 127 Hours. And James Franco is an actor as well as a painter, and he acted in this movie. Yeah, so that's what you see here. There's a director D, a producer D. Person D has the name Danny Boyle. He directed the movie. J is an actor, painter is an actor, and J has named James Franco. Okay. So properties on edges, like let's say, for example, that James Franco acted in the role of Aaron Ralston, they become ternary relations, also known as hyperedges, in graph terminology. So, for example, you see that here, that this is a ternary relation there. Yeah. So in the property graph model, there are also properties on nodes that have collections as values. Like here, apparently, James Franco has his nickname Ted and Teddy. In the relation model, these are very nicely uniformly handled as relations. Like you'll just see that there are separate facts here for the nickname of J is Ted, but the nickname of J is also Teddy. Okay. All right. So RDF can also be represented with relations. So every triple becomes a tuple with the predicate as the name of the relation. So, for example, the name of this painting is the Mona Lisa. So, and the type is painting. So you see here that we put the predicate in the name position of this tuple. And then there's a relation type for it that indicates that this P has type painting. And the name of the painting is Mona Lisa. Yeah. Similarly, it is the creator of this is Leonardo da Vinci, whose name is there, and the type of that is person. Okay. So last, SQL tables can be represented with relations as well. It's good to spend a little bit more time on it because we do this a little bit different than sometimes it's presented. So we like to see SQL tabular data as not very fundamentally different from a knowledge graph. So SQL tables are often represented as a single relation. That's what you see here, like this fact here, which is an order table with customer data and order and price, could be a single relation, but it doesn't look very much like a graph. This is very different from what we've seen in the previous slides, right? So we like to take that table, shape it more like a knowledge graph, where you have a node for the order and then attributes for the different properties of it, and represent that basically in the same way in our relational system as we did on the previous slides. Yeah, so there is going to be a key, 1, and a customer, 500, and a date and a price on this order. Okay. There's one small refinement that I will later get back to, is that we use the table name order as a grouping construct, and I'll explain later what we do with that exactly. That's what you see here. Okay. It's kind of like a named subgraph, to give you a quick hint. All right, so what we have so far hopefully seen is we demonstrated that relations can be used for essentially all data models and that they work great for graphs. I do want to emphasize, I didn't present this to emphasize that we are against tables or RDF or property graphs. They're all pretty useful modeling disciplines. We're just trying to point out that the relational model captures all of them. So if we build a system that is based on a relational model, then we can handle all these different models as imports. Yeah. All right. So next we want to cover a bit, how do we define knowledge for our graphs? So reasoning, as Vinay already greatly explained on Monday as well with graph inference, basically means that we use logic to define how to derive new edges, labels, and nodes. So as a first example, let's take a look at this triangle query, which we'll also use repeatedly elsewhere in other examples. So the query that we're looking for is probably best understood by looking at this graph here, and then here's the first little fragment of rel. So we're looking for a director that directed the movie, and that same director has a child that acted in that same movie. Okay, that would certainly be an interesting situation. Apparently, it happens. And now, so in rel, you basically write it in the same way. It's very similar to Sparkle, actually, at least for this example, is that you just write up the properties of the graph patterns, like D has directed M, A is a child of D, and A has acted in M. Okay. Okay. All right. So a few more examples of reasoning, just to give you a flavor. I don't want to spend too much time on this because Vinay did a great job already explaining that. And what we do is not very different from what was already covered there. But I'll briefly give some examples. Is that here, for example, you can make a spouse symmetric. So let's say there was also earlier, there was a talk from the Wikidata guy in the seminar who pointed out how incomplete the Wikidata graph is. Now, with this kind of definitions, you can complete it. You can, let's say, if spouse is symmetric, you really want to make sure that those axes are symmetric in the graph. You can define it like this. You can also derive new label nodes. So let's say if you have a country code of a country which is the Netherlands, you could label that explicitly as being the Netherlands. Okay. And now, if you know that somebody is a citizen of the country which is the Netherlands, you could also say that that person is Dutch. And now you have a label Dutch, and you can use that in your queries conveniently. Okay. So we do also support aggregations. So this example here counts the number of edges in the graph, and it counts all the edges in the graph. And the next example does this per node, which is the out degree. So it counts the number of outgoing edges from a node X. And then the last example is the most complicated one I have, I think, is a group by aggregation where for every team T, you sum the salary of all team members P. Okay. All right. So hopefully you probably have lots of questions about the precise syntax being used here, which I cannot really explain. Hopefully we'll follow up on that at some point. But I hope that the verbalization is clear and that you kind of intuitively get what these queries are saying. Okay. All right. So for a KGMS, recursion is very important. With many graph queries are actually recursive. Now, usually hello world example of this is graph reachability, also known as transitive closure. So you see that example here. So a node is reachable if there's an edge, and it's also reachable if there is an edge and it is reachable from an intermediate node to B. Yeah. So this is a very simple example. Like most, like SQL support this as well to some degree, and Cypher does in other languages. Now, RHEL supports arbitrary user-defined mutual recursion. So you can define any set of mutually recursive rules that you want. And the recursion can also involve aggregation. So this example here is shortest path, which takes the minimum of a direct edge, like let's say from X to Y, for example, or a shortest path to an intermediate node and the remaining length to get to Y. Okay. And the second path is, for example, here you go from X to T and to Y. Like this path is actually shorter than that path, so you need to consider that. Yeah. So now from a system perspective, there's some, like I want to briefly refer to this, but not explain it too much, is that we actually also can cache and incrementally maintain these results so that when you update the knowledge graph, like so you import new data, so we support dynamic graphs essentially, that this computation is incrementally maintained as well. So we use an approach called differential data flow for this. And if you want to, you can find papers on that. It has been published by other people as well. So, yeah. All right. So what we did so far is that we use constraints that can be used to derive new edges. But often actually fixing a problem is actually not the appropriate solution. And you actually want to have a data integrity violation to be reported instead. So we support integrity constraints for that. They're indicated with this IC. And these will not repair the problem as the constraints did on the previous slides, but they will prevent any change that violates the constraint. So the example is that every actor needs to be a person. So instead of making every actor a person, we're going to give you a violation if you actually do that. Yeah. You can also write that more concisely in an algebraic way. So you can say that actor is a subset of person, and that will enforce the exact same thing as this. You can also say that, let's say, for a parent, that X and Y both have to be a person. It's similar to examples that Vinny also used. And you can say something like that a person should have only one birth date. And function is an abstraction in the library that makes sure that there's a functional dependency on its argument. So you can also define deeper knowledge. Like these are usually captured by schema languages to some degree. Now you can also define things that are arbitrary logical information really that will be enforced. For example, you can specify that spouse has to be symmetric. So instead of fixing it, we're saying that has to be symmetric and this will be violated if that goes wrong. And that located in has to be transitive. And later I'll point out how we use this deeper knowledge also to optimize programs. Okay. All right. So one key difference of graph languages versus SQL is the intrinsic ability to write queries over schema as well as data. It's kind of a mouthful. I'll try to explain what I mean by that. This is very important for knowledge graph applications because you want to explore what relations exist. You don't necessarily upfront know the schema, or you have the schema as a reference that you know entirely. You want to explore what's actually happening. Yeah. So in SQL, you can certainly query the catalog, but you cannot immediately use the output of the catalog query to, in the same query something else as well. And also, like, just querying the catalog is not particularly elegant. It's hard to do. Now, in Sparkle, this is much easier. So you can query, for example, for all the connections that exist from Danny Boyle to Sorkin, which happens to be that they work together on the movie Steve Jobs. So this kind of a schema level query, because the type of relations that exist is normally considered schema, let's say. Yeah. This is a really important feature. I'll show you next how we handle this. It is also kind of the key reason why it is very hard to write something like generic PageRank or similarity algorithms for SQL databases. Because you need to have the ability to generically to traverse edges for this. And there is no superimposed graph for a SQL schema that you can reflect over and execute the algorithm at the same time. Okay, and we do support that. So in RHEL, what you can do is that relations can be grouped into modules. It's a bit similar to named subgraphs. So that is the movie graph here. And the use ... It means that bring all the relations that exist into a movie graph into scope. And then the modules can be queried themselves for what relations they actually define. So you can reflect over them. So this here is the RHEL variant of the previous Sparkle query, where we query for the type of edges that exist between these two persons. Yeah, so that's RHEL1 and RHEL2 is the type of the relationship, and the B is the intermediate node. So it would be the Steve Jobs movie in this case. So we can also use modules as a parameter to generic graph algorithms, what I was just explaining. Like, let's say there's a generic library function called PageRank, and you give it the entire movie graph, and it will compute the PageRank over that movie graph, and the same for node similarity. And you can also abstract over your reasoning rules. Like, let's say if there's a very common pattern to your rule, then you can abstract over that in your logic. Like, let's say if you have information, let's say that the citizenship of a certain country is called something, like let's say citizens of the Netherlands are called Dutch, then you can automatically label, like the rule that I wrote earlier manually, every person as Dutch, and the same for British and so on. Okay. So you can imagine, like, if you refer to the earlier Wikidata talk, the person presenting was explaining how much work it would be to define all these different constraints. Like, in this way, you can abstract over some of these constraints with a meta model. All right. Okay. So we highlighted some ingredients that are needed for expressive reasoning in a knowledge graph system, like recursion, schema level features, and the technical constraints. Now, a key question is, how do we actually make this perform? Was like, certainly you have probably observed that SQL systems do not perform if you give it a knowledge graph application or a graph problem. And it turns out we actually need new join algorithms, and we have been part of inventing those join algorithms. So current SQL-based systems, they use binary joins, which always join two tables at a time. But the problem is that with knowledge graphs, you actually join many relations at the same time, and any binary join order that you choose would have very large intermediate results. So let me try to explain what that means. Is that we're going to go back to our triangle query. It's the exact same query as I showed before. And there are three relations in here. Now pick two. Basically, all the options that you can pick are bad. Like, if you pick directed and child, and you're joining that first, then you're going to have more results than there are directors, because most directors are children, and probably many have more than one. And you haven't really narrowed down your search in any particular way. If you take directed and acted in, that is also kind of bad, because the only thing in common is the M, and every mover has director and actors. So you get a multiplicative effect there. This is not a selective query either. And if you join child and acted in, that's also not great, because every actor has parents, assuming that the graph is complete to a certain degree. And that is also only going to make it bigger. So this problem is one of the reasons why at least practitioners often complain that joins are bad, because they simply don't perform for people in many existing systems. So we try to make them better. Now, to explain that, how these join algorithms work, I'm going to start with a slightly simpler example of joining unary relations, so relations with one argument. And these could be labels in a property graph. So what we're going to do is that we're going to be looking for a female Asian director who is an Oscar winner. There happens to be exactly one of that, one that was awarded this year. And we're going to try to find that person in the data set. Now, in conventional systems, what happens is that you would pick one of these, you would iterate over all the values, and then you would check in the other ones if that is a value that exists or not. So that's expensive to do, because you can actually exploit the sparsity patterns very nicely. Like, let's say in this area, there's no Oscar winner. So you don't have to check any of these people in this area because there's an Oscar winner. In this area, there's no director, so you can ignore all this area as well, okay? So we use something that's called worst-case optimal join algorithms, which is has proven to, it's basically a join algorithm class that is proven to be worst-case optimal. And so there is no better join algorithm that is possible, at least for worst-case scenarios. Yeah. Okay. So I can't really go into the detail of how this works. Like, we'll publish the slides and I'll have some references on papers for it. But one thing you can see is that in 7 steps, we managed to find our Oscar winner, Chloe Zhao. And while otherwise in any other join algorithm where you iterate over one relation, it would take much more steps. Okay. All right. Now that's exciting, but for the unary case, the worst case optimal joins are actually very similar to merge joins, which you may have heard of before in database class. Now the interesting innovation of these worst case optimal join algorithms is that they use this approach continuously while joining relations for all arities. So let's investigate what it looks like. So let's go back to our triangle example. So if we first join on the variable D, then instead of computing the full join of child and directed, we actually only look for directors who have directed some movie and have some child. We're not looking yet for specific movies and specific children. So we're only binding the D, and we're binding it to a subset of the directors because there's probably a few directors who don't have children, and we're not binding anything else. So this is smaller than the number of directors that exist. Okay. So now we have a D, we're fixing that. So we're going to search for known Ds, and now we're going to find A's. And so now we have to find children A who act in some movie. This is very interesting. We're still not looking for a specific movie. We're just looking for a child who is an actor. Now, this is actually a great query because there are probably not that many directors who have children who act, right? There are probably a few, but they're not that many. So this is a very selective query. So this is good. It's better than on the previous slide. And then finally, we connect our triangle by starting to search for the M's. And now we basically, for the given D and A, we're looking for a movie that concretely involves that actor A and the director D. So these worst-case optimal join algorithms, the triangle query is sort of the best example of worst-case optimal joins. They're very good at this. And this approach in general is really good for knowledge graph queries that involve many edges and labels. Yeah. And so we use an just-in-time compiled variant of these algorithms that's called dovetail join. Okay, now what is the impact of this? So let's say, we in our library have a definition of triangle counting, that is this one here. That is a generic abstraction that you can instantiate for a given graph. Now in other systems, like in Cypher, for example, there's a library called GDS that defines all these graph algorithms, but the actual implementation is in Java actually, so it implements a specific algorithm. If instead you do the triangle query in Cypher, because you don't know this, or let's say you don't recognize that your query is actually a triangle query, then you get much worse performance because they don't implement these kind of join algorithms. Yeah. Now, similarly, in TigerGraph, they have a language called DSQL, which at least is not Java, so that's better. It's somewhat declarative, but you're still writing much more of an algorithm. And that makes the system, of course, less accessible for people who don't have advanced algorithmic knowledge. Okay. All right. So here's some references. I'm not going to spend too much time on this, but we'll get the slides published and then you can use it for reference if you want. These first two are written by our colleagues. The second one is now becoming a pretty famous algorithm, which is even finding its way into textbooks, which is great. And the second two are kind of interesting in this context because these are people who have been investigating using these algorithms for Sparkle and even implemented for Jena. And there are very promising results that come out of that. So we'll publish this and the slides, and then hopefully you can read some of it if you're interested. Okay, so what we hopefully have demonstrated to some degree is why worst-case optimal join algorithms are good for graph queries and for reasoning and knowledge graph systems. So now can we maybe even leverage the knowledge that users define to make the system actually work even better? So we're going to look into that. So what I kind of already hinted at is generally our goal is to have users write very high level declarative specifications and not algorithms. We don't want people to have algorithmic expertise. Okay. And our system then uses all the defined knowledge or semantics to make these programs run more efficiently. So examples of this are general mathematical knowledge like associativity and semi-ring properties, for example, but also information that users specify themselves, like functional dependencies or other integrity constraints. Okay. Now, to introduce what this means, I will have a few very simple examples, and we'll look at something more interesting. Is in the first example here, the semantic optimizer is able to determine that f and g are independent because they're indexed by different variables. There's no connection between I and j. Yeah. So it knows also that minimum distributes over addition in that case, right? So that means that we can push things. We can push the minimum down into the addition, and suddenly there's a lot less to compute. Now, in the second example, this does not apply because these are not independent, right? So they both have the same index, and so the optimizer knows that it cannot apply this optimization there. And in the third example, the semantic optimizer knows that the count distributes over Cartesian product that we're doing here, and that instead we can count these separately and then multiply the result. And this avoids then counting an iteration over a huge Cartesian product. Okay, so this is kind of what we mean with this basic ID. So let's see what it does in a more interesting example. So let's say that we wrote a calculation for the length of all paths in a graph. So we have a length relation that is specified between two nodes, and we define recursively how to compute the length, the length of the path between any two nodes. Okay. And then finally, we compute the shortest path by taking the minimum of that computation. Now, this seems great, right? It's very easy to understand. But evaluated as is, this is of course very expensive because we're not only going to compute the shortest path, but all paths and then take the min aggregation. So we use this kind of mathematical knowledge in our semantic optimizer, including in the recursion here, that it knows that we can push the minimum inside of the recursion and distribute it over the addition. And then it actually optimizes the logic into the Dijkstra algorithm. Now, this is very cool, of course. We're applying general mathematical knowledge to derive an algorithm that at some point was actually invented by somebody. Okay. So just for the next slide, note that this defines all pairs shortest path, and we're going to change that. Okay. All right. So next here, just a tiny explanation of how we utilize these as abstractions. There was this length relation here. Now, of course, we actually do not want to tie our algorithms or our specifications to very specific schemas. We actually want to abstract over it. So we support high order parameters, and we just replace length with the weighted edge that we want to apply it to. And then we instantiate the algorithm in that way. I'll show you how we use that next. Okay. All right. So next, to use that, imagine that you want to compute the Bacon number for all actors in a knowledge graph. So if you don't know why you would want to do that, search for 6 degrees of Kevin Bacon. That was a thing at some point where because Kevin Bacon is in so many movies, and kind of like the Erdos numbers, how far away are you from that? Okay. So what we do is we use shortest path, and we give it the co-star graph with the length of all edges set to 1, because we need to assign an edge and a length to it, of course, right? And then we compute the shortest path, but then we only ask in the result for Kevin Bacon. Okay. So now what this will do is it's the shortest path. Remember, it was in all pairs, right? So it will compute the shortest path between all the actors, and then it will select only the ones in Kevin Bacon. So that is not great. What our optimizer can do is it semantically understands this, and it semantically understands that we're only looking for a specific result, and it uses this procedure called demand transformation, which is a little related to metric sets, and then it transforms this all pairs algorithm into a single source algorithm. So that's what you see here. That's the output. So this is specialized both. It pushes the aggregation into the recursion, and it becomes a single source shortest path. Okay. This is very interesting work. We have some papers on that as well. The first two are on these using these semi-ring properties to optimize queries, and the last one is on the demand transformation. And again, you can look this up later from the slides. Okay. All right. So so we've gotten some intuition now how we can use like deep knowledge of application logic to derive essentially efficient algorithms from declarative specifications. Now, of course, every single data application out there actually uses some aspect of machine learning. So how do we support that? It turns out that at least REL is...
So Martin, we've got roughly 5 minutes.
Okay, thanks. Yeah. So REL is a great language for feature transformations. Like it is, as you can probably have gathered by now, it is not just a graph query language. It's actually more like a language for mathematical notation. The standard library of REL already includes many standard transformations. Like, for example, like the triangle count and shortest path is in there, but also something like z-score normalization, which defines a normalization that people often use to get better inputs into their machine learning algorithms. And now what's cool is that these feature transformations, they benefit from the exact same semantic optimizations that we just explained and incremental maintenance. So you can define your transforms, and then if you edit your input slightly, it will only incrementally recompute what needs to be recomputed. Now the library also defines prediction and cost functions like MSE and RMSE. So these are defined in the language itself, as you can see here. And if you kind of squint, you can sort of recognize this mathematical formula for it. Because the entire cost function is declarative, mathematically defined, we can fairly easily take the derivative of it and then train that with gradient descent, which is what we do. Yeah. So what you see here is that we instantiate the cost function with a very simple example of a linear regression prediction function with some feature set. We give it in this case, it's about life satisfaction. So we give it the life satisfaction expected values, and then we can actually train that regression model and get weights out that we can use. Yeah. Now, this is there's some fascinating work here that I absolutely do not have time for to explain today, but we do not actually do this by creating a design matrix, but instead we actually operate directly over the relational structure and exploit these semantic optimizations that I just mentioned. I have some really good links for that next, and so there's also a talk on that separately, so I would refer you to that if you're interested in that. Yeah. Now, so we can also, to some degree, dabble in deep learning. So we already in our company, of course, use graph embeddings and graph neural networks, but currently this happens in external tools, very similar to what you would do with any other existing graph database like Neo4j and TigerGraph. However, the language is actually in principle expressive enough to actually even describe the neural networks. So our ambition is actually that at some point we will be competitive with those tools on training neural networks mathematically defined in REL. So we support defining activation functions, which you see here, and we support computing the activation, and we support training of it. The challenge is just that currently we're focusing mostly on sparse data, particularly graphs. The Western optimal joins are great for that, and this is always dense data, and that's not currently what we're optimizing for. But what's cool is that this is actually exactly what the relational model is intended to do. Like it claims that the application logic should be independent of the physical representations. So if we get better at evaluating this, then at some point this will hopefully be competitive in performance as well. So these are the references I referred to. So there's some videos here of talks. One particular cool thing is that one PhD student that was a major contributor to this work, he got the honorable mention in the Jim Gray doctoral dissertation award. That's very exciting. So there's quite some recognition for this work in the database community. All right, so that was it. So the capabilities that we covered are in this area. Now there's a lot of other stuff that is also really cool about what we do that are more system related, like around versioning and temporal capabilities and data ingestion and sharing of models with other people. But I don't have time for that. If you love all this stuff, like first of all what I presented, but maybe also the system capabilities, we are hiring. So feel free to reach out if you're interested in any way. That's it.
Thanks, Martin. That was an awesome presentation. So we're going to move to our next speaker. Jiaoshang, over to you.
Can people see my screen?
Yes, we can see your screen.
Okay. Let me pull up. Okay. Thanks, Winnie, for introducing me to this lecture. So my name is Jiaxuan You. I'm a fourth-year PhD candidate from Stanford University. Today, I'm going to give an high-level introduction to graph neural networks So I will talk about why do we need graph neural networks, what is a graph neural network, and its applications. And the slides I'm presenting are adapted from CS2 a course that I was a head TA. And if you want to learn more about it, welcome to take that course. So as we know, many types of data are graphs. Throughout this seminar, you probably have seen a lot of knowledge graph examples, and there are other real-world data that can be represented as graphs, such as biological regulatory network, scene graphs, code graphs, molecules, where the atom and the bonds are nodes and edges, or 3D shapes, where it's a 3D mesh defined by a graph. The main question we want to ask here is that how do we take advantage of relational structure that can help us make better prediction? So we're going to discuss this through the language of machine learning. So we know that these complex domains can be represented as relational graph, and then we'll explicitly model these relationships and in order to achieve better performance. So we know that modern deep learning toolbox are designed for simple sequences or grids. So for example, we can have this convolutional neural network for the image data. It can be applied for, say, face detection. And we can have some recurrent neural network or transformer for text or speech data, and they look like sequences. But networks or graphs, they are more complex. So specifically, graphs could have arbitrary size and complex topological structure. And it really doesn't have any spatial locality like grids or sequences. The key concept we'll discuss is the node embeddings. The intuition is that we can map nodes to d-dimensional embedding space, such that similar nodes in the graph will be embedded closer together in the embedding space. So more specifically, we will have an input graph, and we want to learn an embedding function f, such that we can embed the graph into some low-dimensional node embedding space. And later, we'll discuss how do we learn this mapping function f. So to be more specific, our goal is to define two things. First, we'll define an encoder that can encode the input network into some d-dimensional embedding space. And then we'll define some similarity defined over an input network so that we can train the embeddings to approximate such node similarities. So as we just discussed, there are two key components. The first is an encoder that map each node to a low-dimensional vector. The input will be a node in the input graph, and the output will be d-dimensional vector embedding. The second notion is a similarity function that specifies how the relationships in the vector space can map to the relationship in the original network space. So the similarity could, for example, be as simple as just a dot product, which measures the similarity between two nodes. So one simple example for encoder is the so-called shallow embedding or shallow encoder. So here the encoder is just an embedding lookup. So let's say we have an embedding matrix Z, and each row will correspond to one dimension of the embedding, and each column will correspond to one node. So let's say if we want to get embedding for the fifth node in the graph, we'll just look at the fifth column of this embedding matrix, and that vector will be the node embedding for that specific node. And the point I'm trying to make here is that a knowledge graph is usually just a shallow encoder plus some similarity decoder. So the edges in knowledge graph are represented as some triplets. So it has a head, relation, and tail. To learn knowledge graph embeddings, people usually first want to define a shallow encoder. Basically, they want to model entities and relations in the embedding space. And this is really done via embedding lookup. So each entity and each relation is associated with a shallow embedding. And then having do this shallow encoder, people will do similarity-based decoder. So give a true triplet head, relation, and tail. The goal here is that we want to use the embedding of a head relation to be close to the embedding of the tail. So a famous example is the Trans-E model. So here, people use the translational intuition, where for a triple HRT, they are in the embedding space. We want to have H plus R approximately equal to T if the given fact is true. And if the facts does not exist in the knowledge graph, they won't be equal. And how do we learn such relationship? This is usually done through a scoring function. So we want to minimize the distance between the head plus relation and the tail. So for example, if we start by a node, say Obama, and we'll move in the direction of the embedding of nationality, eventually we can read another node that is American. So these kind of shallow encoders really work well for knowledge graph applications, but it does have some limitations. So first, really here we need the order of number of nodes parameters. The reason is that there's no weight sharing of the parameter between nodes, so we need to assign a unique embedding for each of the nodes. And secondly, it is inherently transductive. So what does it mean is that it cannot generate embeddings for nodes that are not seen during training. So imagine you have a knowledge graph, and then there are some incoming new entities and new relations. Usually you have to retrain your system to learn the embedding for them. And finally, this methodology cannot incorporate node features. So usually nodes and edges, they are always just represented as IDs, and it is unclear how you can directly use the node or edge features. However, in real life, many graphs do have some features, like some user profile features or some relation features. So today I'm going to introduce some deep graph encoders, and then we show that in fact these graph neural network based methods can overcome these limitations. So more concretely, we'll introduce a class of this encoder of the nodes that consists of multiple layers of nonlinear transformations based on the graph structure. And one note is that all of these deep encoders can actually be combined together with the node similarity functions defined in knowledge graph methods. And visually, this is what is happening. So we'll have a very complex input graph. This graph will go through different layers of graph convolutions, and then the output will be node embeddings. And in the meantime, we could also embed subgraphs in the same process. So we have just talked about why do we need graph neural networks. Now I'm introducing what exactly is a graph neural network. So here's our setup. Assume we have an input graph G, where V is the vertex set, A is the adjacency matrix, and usually just a binary matrix of zeros and ones. X will be a matrix of node features, and V is a particular node in the graph, where NV defines the set of neighbors for a given node. So here we assume node could have some features. For example, in social networks, user profiles will be some user features, user images, for example. And then say for biological networks, we could have some gene expression profiles or gene functional information. So these are some useful node features to have. And there are some cases that we don't have any node features. There we can use some simple alternatives, for example, indicator vectors. So we have one hot encoding for each node, or we just assign some constant vector for all the nodes. So a naive approach here is really just concatenate this adjacency matrix and this node feature matrix, as I have shown here. And then we can feed such combined representation into a deep neural network, such a very simple linear multi-layer perceptron, for example. The issues with this idea is that it will require a number of parameters to the order of number of nodes. It is not applicable to graphs of different sizes, and it is also sensitive to node ordering. So the idea of graph neural networks is really inspired by this popular convolutional neural networks. So imagine this is how people will apply a CNN on an image. So people will define some convolutional filters, and then we will convolve these convolutional filters throughout this image. And our goal here is to generalize this convolution defined by images into some more general settings. And in the meantime, we want to leverage node features and attributes. So our graphs looks quite different from images. It looks like it's just very complex shapes. And also, there's no fixed notion of locality or sliding window on the graph. It's a bit harder to define compared with learning from lattice images. So here's our key observations that can help us translate models from images to graphs. So here I show an example of a convolution neural network with 3x3 filter. So you can see the output pixel is really depending on the neighbors pixels surrounding these pixels. So this intuition can generalize to graph as well. So if we want to learn an embedding for a given node, we could make use of its local neighborhood. So using its adjacent nodes. And the idea here is that we can transform information at the neighbors and then combine it so that we can get the node embedding. So more specifically, we will first transfer messages hi from the node neighbors through, for example, some linear transformations, and then we'll add them up. And then this will be the final node embedding we could have. So now I'm going to introduce the concrete graph convolutional neural network or graph neural network. It's really just consists two steps. So first, we want to determine the node computational graphs based on the node's neighborhood. And then based on the computational graph, we'll propagate and transform information throughout the graph. So here's a more concrete example. Suppose we have this input graph, and our goal is to learn embedding for this target node A. We'll first generate node embeddings based on the local network neighbors. So A has neighbors B, C, and D, and we'll write them here, B, C, and D. And then for each node, we'll look at their neighbors. For example, B will have neighbors A and C, and so on. So our intuition here is that we want to apply some neural networks in this aggregation process so that we can compute embeddings. And a very interesting observation here is that you can see that every node will define a different computational graph based on its own neighborhoods. For example, the computational graph for A, B, C, D, etc., they are quite different. And this way, we will be able to learn different embeddings for different nodes. And this computation is really happening in many layers. So nodes could have embeddings at each layer. In the beginning, the layer 0, the node features will be just its input features XU. And then we'll apply rounds of message passing or aggregation. So based on the 0th layer node features, we'll get the first layer through one hop of aggregation. And then we'll continue doing this aggregation. Eventually, we can get this embeddings for node A that we want to learn from. Then you see that the case layer embedding really gets information from the nodes that are k hops away. So through one layer, A is able to get his information from one hop neighbor, and through two-layer computation, it can get information from its two hop neighbors. And the next, I'm going to talk about how do we really define this black box. So a basic approach here is that we will average information from neighbors and then apply a neural network. So you can see that the first step is to average messages from neighbors here. And then using the average messages, we'll apply some neural network. And here is the math that is happening. So first, we'll initialize the 0th layer embedding using the input raw node features XV. And then for each layer, the input will be embedding of nodes at the previous layer L. we'll average the neighbor's previous layer's embedding to compute the message for this layer. And after the computation, we will apply some matrix transformations, W and B, where this W and B are weight matrix of the graph neural networks, and they are trainable. After computing these messages, we'll finally apply some nonlinearity to increase the expressive power of the GNN. And we'll repeat this process for L rounds, where L is the total number of layers. Eventually, we'll get the final node embedding for node V, and this is computed through these L levels of GNN layers. And having defined this GNN, the next question is that how do we train a GNN? So we have known that this GNN provides us the node embeddings ZV. There are two general settings to train a GNN. The first is a supervised setting. So we want to minimize the loss between this node embeddings and some targets, Y, where we want to optimize the parameter setup that is defined in this graph neural networks. So what are possibility of Ys? It could be some node level labels, edge level labels, and graph level labels. These labels usually come from some external sources, and I will give some concrete examples in the next section. And the loss function is pretty standard. So if Y is a real number, we'll use some L2 loss. And if Y is categorical, we'll use some cross entropy, those classification loss. Another setting is unsupervised learning setting, where instead of using some external source supervision labels, we'll use graph structure itself as the supervision. For example, we can define some node similarity based on the random walks, or we can even use some knowledge graph objective defined by, say, trans E or rotate E, etc. So here is an overview and summary of what we have talked about. So this is how a graph neural network will work. So first, we'll define a neighborhood aggregation function, and then we'll define a loss function on the embeddings. We will train these embeddings based on a set of nodes, for example, a batch of computational graphs. And then having got a trained model at test time, we'll generate embeddings for the nodes as needed. And the cool thing here is that we can even generate nodes that we are never trained on. So this really resolves the problem of not inductive. So now I have introduced what is a graph neural network. In the final section, I will talk about some cool application of graph neural networks. So there are several important tasks that can be defined on networks. So using a graph neural network, we will be able to solve, say, node classification, where the goal is to predict a type or some labels of a given node. We could define some link prediction task, where the goal is to predict whether two nodes will be linked together in the graph. And we can do some community detection task, where given the input graph, we want to define some interesting community structure in the graph. And finally, we can do some graph classification tasks, where the goal is that we want to classify different graphs, for example, classify different molecules. So I'm going to introduce node level machine learning tasks using graph neural network first. So the first example is to do protein folding. So a protein chain really acquires its native 3D structure from a sequence of amino acids. So we have this information of a sequence of amino acids, and in the end, it will fold into a 3D structure. And the protein folding problem is that we want to computationally predict a protein's 3D structure based solely on its amino acid sequence. So here are some very cool predictions made by DeepMind AlphaFold team. So you can see that their predictions are pretty close to the ground truth of 3D structures. And how did they do it? So they really use the technology of graph neural networks. So their key idea is to build a spatial graph where the nodes are the amino acids in a protein sequence, and the edges are the proximity between amino acids, and this is measured in the 3D space. So having defined such a spatial graph, they will apply some technology pretty similar to graph neural networks to make the prediction. So we have seen the node level task. Next, I'm going to introduce edge level machine learning tasks using graph neural networks. So a very important application here is the recommender system. So a recommender system can be considered built for a user-item interaction graph. So for example, a user may watch some movies, buy some merchandise, listen to music, etc., where the nodes are the users and items, and the edges are their user-item interactions. Our goal here is to recommend items that users might like. So for example, we have this user nodes and this item nodes. We know that the users may click or interact with certain items, and the goal is to predict the future. Like you might also like this T-shirt, things like that. So a very successful approach here is called pinsage, that use graph neural networks to build a successful recommender system. The task here is to recommend related pins to users. So for example, we can have a query pin that is a cake, and a successful recommendation will recommend another cake, where a bad recommendation will say recommend this T-shirt with sleeves. And our objective here is that we want to make the embeddings between two cakes closer to the embedding between a cake and a sweater. And if we train graph neural networks using this edge level prediction task, the model will be able to predict whether two nodes in the graph are related. And this is really a core component of a recommender system. And next, another successful application will be applying GNNs to subgraph level machine learning tasks. So the example here will be to do some traffic prediction. So suppose if you open up a Google map and you want to navigate from, say, Stanford University to UC Berkeley. So here, the underlying representation is also a graph, because you can treat a road network as a graph where the nodes are the road segments and the edges are the connectivity between these road segments. And people will be able to make traffic prediction based on the road networks. And the technology here is also a graph neural network. This technology has been deployed in Google Maps, and it seems that it's performing pretty well. In the end, I will talk about the last examples of graph learning tasks, that is using GNNs for graph level machine learning tasks. So here the example is drug discovery. So antibiotic molecules are really some small graphs. Atoms and edges are chemical bonds. So here I show some example molecule graphs here. And people have successfully using graph neural networks for antibiotic discovery using this graph representation. So this is a really high impact paper published in Cell last year. So they formulate the problem as a graph classification task, where the goal is to predict those promising drug molecules from a pool of existing candidates. And another interesting perspective for this problem is to do molecule or graph generation, where we'll generate novel molecules, and potentially these new molecules can be used for drugs. There will be some very cool use cases. For example, we could generate novel molecules that can have very high drug likeness, or we can optimize some existing molecules to have some desirable properties. And the underlying model here are all graph neural networks. So to summarize, today I have talked about the motivations for graph neural networks, that they are expressive and scalable. I have talked about what is a graph neural network. So the key to define here is a node neighborhood aggregation function. And then we also need to define some losses and training procedures. And finally, I have discussed some cool application of GNNs, and they are really happening in different levels. They can be node level, edge level, subgraph level, or graph level. And as I have talked before, we have more materials in the course Stanford CS224W, and here's are the resources. Thank you.
Thank you, Jukshaw, for that overview of graph neural networks. We have now about 20 minutes for discussion and questions. So it doesn't look like anybody in the class has asked questions. So maybe I'll start by asking a question. Martin, I was curious to know how do you actually implement the shortest path algorithm? So in Tuesday's lecture, we talked about this A* search for calculating shortest path, and you were showing that you could formulate shortest path queries using your query language. So what happens? I mean, are you using a join algorithm, or what's really going on underneath?
Yeah, it is. Yeah. So there's a few different aspects to it. So one is that the example that I showed was that from a path computation, you compute the shortest path. So that's very logical, right? So the actual evaluation of the computation will happen with joins. So let's say the edge relation and the shortest path relation will be joined. So there is some particular aspect to it that we're working on where you need to evaluate the recursion in a certain way that it actually does have the exact complexity of the Dijkstra algorithm. So we're working on a paper on that with Dan Sucio. So that is upcoming. So there's the logical aspect, and then there's the joints, which are in this case worst case optimal joints, and then there is how you actually do evaluate the recursion, which I didn't really go into in the current talk. So yeah. So
again, I didn't quite follow your answer. I mean, is your implementation equivalent to A* search, or no? It will be. Yeah, I think so. Yeah. Okay, but right now it's not. Due to the recursion thing, yeah, that's what I understand. At least I'm not like I'm a PL database person. As a person on our team, Hung, who is the sort of the algorithmic complexity person, and so he tells me that this aspect is still needed to get entirely there. So yeah, and but the good thing is that like the way that that recursion will be implemented is basically for any type of recursion. So any other problems that we will be implementing will have the same benefit, basically. So yeah. Okay, well,
I have a question for
Go ahead. Go ahead.
So do you have any examples of, so first of all, that was a very good set of applications that you showed from graph neural networks. Any application in natural language processing to figure out semantics of words, etc., that you have worked on?
Yeah, thanks for the question. So you're asking some good natural language processing applications of graph neural networks.
Yes.
So I personally haven't worked on that aspects, but I have heard of very interesting works there. So usually people can combine this knowledge representation, some structured natural language data sets with some unstructured data, such as some bird or those kind of models together, and they can probably train end-to-end, etc. So I think my takeaway is that as long as you will be able to define those entities and relations, you will be able to apply graph neural network on top of it.
Okay, thank you.
Yeah, no problem.
Okay. So we have an audience question. Do graph neural nets map well to other parts of the brain or other streams or systems?
Yeah, I think that's a very interesting question. So it seems like the audience is asking like how can we draw analogy between brains and graph neural networks. Yeah, so I'm a typical deep learning guy, so I don't know too much about neuroscience. But my understanding is that some similar patterns may probably also happen in the brain. So I have talked about the core of graph neural network is to do message passing. And we know that maybe in the brain, the neurons also pass messages, and there will be some aggregation and transformation there. So I think in that aspect, we are also really inspired by how the brain is working. I hope that I can answer the question.
Cool, thank you. So there are a couple of other questions that just popped up.
While you're processing those questions, I have a question for Jiapchon. So recently, Michael Genesreth got a recommendation from Amazon that he should buy the textbook called Introduction to Logic. And he happens to be the author of that book.
So, it was a good recommendation myself, but
right, it was a good recommendation, but I don't think it was going to lead to a sale for Amazon. And I don't know. Do you have any insight into how these recommendation systems could actually be more smart about the real world knowledge?
Yeah, I think that's a pretty general question. I think nowadays, most recommender systems are not really graph-based. So people may still use those traditional recommender systems like those collaborative filtering, those matrix factorization kind of techniques. So graph neural network is really new in this direction. But based on my experience, I feel like this kind of deep learning methods, they do have some potential benefits here because you will be able to use more features there. So for example,
again, I think, so, okay. So I mean, in this case, the feature or the additional piece of knowledge we want to give to the system is that if a person is the author of the book, then don't give that recommendation, or that's not a good recommendation, right? So
yeah.
How would you actually incorporate that into a graph neural network?
Yeah, I think my understanding is that for deep learning type of models, people will do fewer hand engineering. So potentially we cannot directly inject those rules in the models. But if we have abundant those buying activity data, so let's say if we know that Michael is the author and he won't buy this book, this kind of training data may inform the models, and next time it won't make such kind of recommendations.
Okay, so your answer is give training data, right?
Yeah, I think usually, yeah, deep learning model really require a lot of data to work.
Okay.
Can I briefly comment on that? So we work with Guy van der Broek, who has also been working in this exact area. So like basically combining neural networks with logical extensions of it, so that you can have some reasoning component in it. I'm personally not an expert in it, but if I would want to read about it, I would go there probably. So basically combine the benefits both of the neural networks with like some logical sanity, like Michael shouldn't buy his own book, let's say. So.
Thanks. So there's a question about scalability of the GNNs. Can you comment on that?
Yeah. So talking about the general scalability of GNNs. So in the paper, one of the paper I talk about called PinSage, people really deploy this GNNs in the Pinterest product graph, which consists of, I don't know, maybe billions of nodes and edges. So I think that's a really large scale industrial application. So I think there's no real like algorithm challenge there. It really depends on how much resource you want to put there.
Okay, thank you.
Yeah.
And there's one more question about some supervised versus unsupervised techniques in GNNs and any difference in performance you've seen.
Yeah, I think that's also a pretty general question for machine learning. I think based on my experience, usually as long as you have some supervised signals, you will most likely getting better performance because you can get some task-specific predictions. But really to make a system work, some kind of unsupervised regularization is also pretty helpful because in that way you won't overfit, especially in some high-stake applications because the training data is really scarce. So you probably will start by pre-training your model using some unsupervised objectives, and then using the pre-trained model to fine-tune on your supervised learning tasks.
So Martin, going back to the previous question about scalability, do you all have some results on how you can scalably implement neural net computations using your engine?
Yeah, it's an interesting question. I'm glad you asked because I was exactly thinking about that question. So we do this for relational machine learning, as in non deep learning. So let's say if you train a shallow model, then we can incrementally maintain the training as well as the feature transformations that you do before it. So that works well. Like Dan Oltiano, who we work with, has written a bunch of papers on that as well. So for deep learning, we have not done that yet, but it would be very interesting. Like in principle, our system supports it because we describe the end-to-end pipeline. So the provenance is entirely clear, and we have incremental maintenance that is generally applicable, should be incrementally maintained, right? It's just like it always depends on the exact problem, how incremental it actually is. Like if there's a lot of dependencies where everything scatters everywhere, then it would not be incremental, right? So it depends on the actual issue, and we don't have yet complete experience with doing that for neural networks. But in principle, it would be interesting to try, to explore. Yeah.
Okay, so Naren, as you're processing the questions, I can ask another question from Jiaxuan. Sure. What is your thought on whether feeding the graph structure into a machine learning always helps? I mean, are there situations where giving it domain knowledge in the form of graphs actually is harmful, or it deteriorates the performance?
Yeah, that's a tough question, I would say. I think in that sense, you probably want to specify your pipeline or model well. So for example, you could consider adding both passes to make your predictions. So for example, one pass is a model that does not use graph neural networks. Another pass is to use graph structure. And if you can consider this like a voting system or some attention mechanism happening there, so if the graph component is harmful and not useful, the model may choose not to use that information. So hopefully, at least by adding graphs to your system, it shouldn't make the performance bad. But I do agree that in certain cases, graph structure may not help too much.
Cool. So there's a question for Martin, a long question. So Martin, one of the advantages of using semantic data structures and one of the weaknesses of relational data structures is that the former can accommodate a much richer palette of predicates than the latter. Since relational databases are based on set theory, they really only handle the is a relationship. How does your database deal and accommodate with a richer selection of predicates? Are they stored within some sort of predicate column in your database? So some implementation, someone is asking for some implementation level.
Yeah. So I understand the first part and the second part separately, but not necessarily the combination. So I'll try to comment on it together. So we are focused on making extremely scalable systems. So let's say there are, of course, like tier improving solutions where, let's say, you can prove very strong properties based on very general logic, but that doesn't scale to very large sets of data. And we do want to make a system that scales to large sets of data. So that's a choice. Like, and there's always room for tier improving, of course, right? We second, like our language is designed to support more some kind of meta programming in the reasoning language. I showed a brief example of that. So you can indeed actually meta program over relations, but in the end, it is only a shorthand for writing a lot of logic, basically. Like that doesn't enhance the expressivity. It is just to allow you to quickly define large swaths of logic if you have to define that. So then the scalability becomes more in how much logic are you going to generate, and can it still efficiently reason over that? So yeah, so we do support that kind of meta program, and you can get quite far with that. But we would have to look at concrete things that you're thinking about, whether that actually scales to this kind of approach.
Okay, sounds good. And here's a question that probably bridges both your talks. So after you go through the whole computation, what is the GNN's persistence layer? Is it a graph DB or an RDBMS or just a file system? So maybe Martin, you can.
Martin or Jiakshan.
Yeah.
I mean, it's GNNs are probably currently using just a file system, right?
Mm-hmm.
Yeah. So in our case, it would be in the database, like it would be in a relation, with everything is a relation, including the graph neural network model. But that's not current practice, yeah. Like so, but that's what we do. Yeah.
Yes, so I think it can just be stored in a key value pair. Then I think you need more advanced structures to do fast nearest neighbor search, like a KD tree, the system that implements KD trees, hashing. So I think a lot of different, based on your application, I think there are a lot of different backend databases or storage systems that you can use.
Maybe an interesting related, like I'm actually not sure if I understand the question. If he's asking about understanding the model or in which kind of tool you would actually store the graph that you're operating on. So it might be interesting to know what tools are in common use in these graph systems, maybe. Yeah.
Well, so I mean, some of these deep learning models, the model that itself is like gigabytes of data.
Right.
And it gets stored in a file system. That's sort of what I've seen done. Martin may say that, no, we can store it in a database, but that's certainly not the state of the practice right now.
For word embeddings, we have applications that we just store things in like a hash table, and then we need to compute really fast nearest neighbor techniques, and we do that in various different ways. One is like brute force O of n. There are some, then we use KD trees, hashing techniques, etc.
Yeah, so there's this question about what role does hardware optimization play for GNN type applications? Jiakshan, you have any take on this?
Yeah, I'm also not really a hardware guy, but I do know some progress or like attempts being made here. Because graphs is really a sparse data structure. So if you have a hardware that can do really efficient, say, sparse matrix multiplication, that will really help a lot. So compared with using a generic GPU.
And your algorithm is quite parallelizable, right? It can compute different things, you can distribute it over all the GPUs, so it's highly parallelizable.
Yeah, it's very parallelizable. So you can parallelize your computation over the nodes. So imagine you have a million nodes, you can compute their embeddings in parallel.
Yeah, mm-hmm. I think that would make use of the GPU structure very well.
Yeah.
So I actually have a question for Mike, that after seeing Martin's presentation, do you think triples are a more viable technology for storing data?
Well, that question is laden with some connotation, which it suggests that I didn't think so beforehand. And I would certainly not be there, since many of the systems that I have built have been triple-based systems for some time now. I have criticized triple-based systems on the grounds that they are more expensive because they require that joins be done. There is a certain amount of data access cost that one pays, but the flexibility one gets from having triple-based systems is quite good. And when we have good algorithms like the ones that Martin was talking about for dealing with these joins, it ameliorates the problems to some extent. I'd still say that if I have a choice between a wide table and a bunch of triples, and there were no other considerations, I'd still take the wide table. It's just cheaper. But certainly I would like to have I like the flexibility of triple-based systems. So I hope I've hedged my answer sufficiently that nobody knows what I actually think.
Yeah, I mean, I think one interesting example Martin had in his slides was that when you have the triple-based system, it is easier to query the schema itself. If you had a wide table, then you would probably need some way to put the schema information in the table itself so that you could query it, or you would have to provide a different operation using which you could.
Yeah, we might be down in the bits and so forth. I mean, obviously every SQL database has a schema database as well that you can query, and you can do joins between the schema database and the base state level databases too. It's just that it isn't as convenient and as uniform as it is in Martin's system. So I agree that that's good. It's not as it can't be done, but I do like the uniformity, the simplicity of the triple based approach. Both triples are easy to think about and easy to extend. You want to have another column, you don't have to make your table wider. You just throw in another relationship. There's no question that that's good. But it's not as if it's something can't be done the other way. It's just that it's something that I would prefer not to do if I didn't have to.
Right. Okay, so we are pretty much at the end of our class time. So with that, I'd like to really thank both Martin and Gyeokshon for taking the time out, for speaking to our class, telling us about their work and inferencing, both using join algorithms and using graphs and neural networks. So it was really very insightful. So thank you both very much. So we'll conclude today's session here. And as far as the class is concerned, we'll continue next Tuesday. The focus for our discussion next week is going to be on how do users interact with a knowledge graph. Thank you all very much, and we'll see you next week.
Great.
Thank
Thanks
you.
to the speakers. Good talks.
Thank you.